Greetings, everybody. Welcome to Peace Engineering Echo Collaborative. Let's wait while people connect. While you connect, if you can type in your name and affiliation on the chat, that'll be awesome. Let you know that this session is being recorded. Type in your name, email in the chat. If you're not talking, please mute yourself so we don't introduce background noise. And then we will have a Q&A session after the presentation. I'd like to share this slide with you. There's been several calls from the United Nations Secretary General on peace and nature. We really need to make peace with nature. So it's a call for everybody to really start working on the 17 SDGs, especially climate change is a major issue. Next slide, please. So this is a definition of peace engineering. This movement was started in November 2018 after we organized the first global peace engineering conference in Albuquerque, New Mexico. So this is a definition. There's others there, but this is the one we use. Next slide, please. So today we have Dr. Peter Lilienthal, who's going to give a collaborative talk on the Peace Engineering Echo. He's the founder of Homer Energy. Also, he's the lead for the Global Microgrid, which is part of the Underwriters Laboratory. He's been involved with NREL, which is the National Renewable Energy Laboratory. His expertise is in renewable energies and software optimization. So it's an honor to have Peter here. Next slide, please. Peter, I'll pass the microphone to you so you can introduce yourself and talk a little bit about your background.
Sure, thank you. And thank you all for attending. As he said, I'm Peter Lilienthal. Back in 1992, as a response to the Earth Summit in Rio, NREL was asked to come up with a program to help developing countries use renewable energy. We created the Village Power Program, and as part of that program, we needed a model, a software, to design what those power systems would look like for the billion people in the world who don't have access to modern electricity. So it was a great opportunity for me to use what I learned in grad school about optimization technologies, et cetera. So I created this optimization tool. At first, it was just a internal research tool in the early 90s. This was really a research project. But in around 97, we converted it from, it had originally required specialized optimization software, ran on a Unix workstation. There was only one or two of us that could actually use it. We converted it to a Windows application with C and C++ and put it up on the web. And it was about that time that there started to get more and more interest in some pilot projects happening, building these hybrid renewable microgrids or mini grids for energy access in developing countries. So that was, we called it the Village Power Program at the time. It sort of ended in the early 2000s, as politics changed, et cetera. But the World Bank kind of picked up on it, and it morphed into what is now the Global Village Energy Program. But I kept Homer going at NREL and expanded it to do larger systems like not just small village systems, but whole islands or whole remote towns. And then in 2008, we spun it off to be part as a private company. The National Lab is a great place to do research, but it's not a great place to commercialize things or to support software users. And at that time, we were now getting thousands of users. So we created Homer Energy. Actually, I have slides for this, so I'm going to put them up now. Well, here, I guess there's one more slide here. Right. But that's sort of my opening slide as well. So actually, sorry, I should have done that. So there's just a little bit of the history that I was just referring to. So since we've become a private company, it really expanded around the world. You can see on the map, those are places where they have modeled microgrids using Homer. So we have over 100,000 people who have get our newsletter. I'd encourage you all to sign up for our newsletter. Go to our website, homerenergy.com. And we have a lot of data around of how microgrids are being used around the world. What we're going to talk about today is powering health. So this is a little different. The main Homer software are desktop applications, but we've created web apps that run those run Homer on a server, and so you don't need to download it, and they're much simpler versions. The original Powering Health was created with funding from USAID. PEPFAR stands for the President's Emergency Program for AIDS Relief. So that was 13 years ago. And then in the spring of this year, the World Bank contacted us and said, let's update that for COVID response. And so what I'm going to show you is the updated version of that. And just a little background on what Homer is. It's an optimization software. And you need to know things like fuel prices and interest rates, et cetera. For the economics, you need to know the load profile. That's the main thing I'll be showing, actually, is how to generate that. You need to know what the site-specific renewable resources are, which we have a global databases of renewable resources. So that's just click on a map and that's easy. And we have a library of equipment. For this simple web app, we generally just use generic equipment, but you can then download those results, look at them in Homer in the more powerful desktop versions, and and then we have a extensive library of different batteries and inverters, et cetera. Anyway, those are all the inputs. And the way Homer works, it simulates the operation of a power system for an entire year, or actually up to 30 years if you want, but for this web app, just 1 year. In hourly time steps, we can go down to 1 minute time steps in the desktop product. How is that system going to operate? How much, if it has a backup generator, how much fuel is it going to use? How much are the batteries going to get used? Is the loads going to be fully met, et cetera? And that tells you what it's going to cost to operate, to build and operate that system. That's one system. Then it will do that same simulation for hundreds of potential systems and rank them by cost of energy or net present cost to find the least cost system. You can you can rank them in other ways as well, but that's the main way to tell you what's best for a particular scenario. And then there's sensitivity analysis, because oftentimes there's a lot of uncertainty about things like fuel price, but also the loads and the prices of equipment, et cetera. So sensitivity analysis is really important. So these are sort of nested do loops in computer speak. And we have two versions. Homer Pro is the original sort of flagship version. It's kind of a Swiss Army knife, does all kinds of things. That's what you want to use for off-grid systems, and that's what the web app I'm going to show uses. But we also have a newer version just for grid-connected microgrids. And then you get all kinds of results, and I'll show examples. The main one is, what's the least cost system look like? What's the size of different components? But also things like cost of energy, internal rate of return or return on investment, et cetera. You can drill down and see hour by hour, how did the system actually operate, and it will produce a proposal or reports. So that's an overview of how the system works. I think that's my last slide. So I'm going to switch screens here and show the actual app. So if you go to on the web and type in poweringhealth.homerenergy.com, this is where you get, and we've got a lot of information here to help you. These little arrows tell you, show that there's more there. This guidance note is quite substantial. Oops, wait a minute. Oh, sorry, it's down here. Well, it's a Word document with lots of information about hopefully you can see this. But I'm not going to go through it. It's a very long Word document with lots of information about the energy requirements for remote health facilities. But what I want to show is how to use is just walk you through the tool. So by clicking on a map here, you get resource data for that location, and you can zoom in and scroll around, etc. Now it will work for grid connected or off grid systems. For the grid connected systems, we're assuming this is remote, and maybe there's a diesel power system but maybe it doesn't run all the time. It only runs in the evening or whatever. So you can say it turns on at a certain time, runs for 6 hours, etc. For this, I'm going to assume there is no grid. And some very simple assumptions about what's the cost of fuel, the cost of different equipments. These are all editable. So if you say, no, actually the cost of fuel is a lot less than that, they're fine. You can look at two different kinds of batteries. And again, after you're done here and you want to look at it in the desktop, you can look at all kinds of different batteries. Don't necessarily take our word for the price of these things. These are just default values. You can edit them. And here's the bulk of the web app is defining the load profile. We have 4 sort of templates or archetypes of what these different size facilities, what kind of equipment they have and what kind of power requirements they have. We worked very closely with some health experts at the World Bank, in particular Chris Purcell and Alan David Lee, who have a lot of experience mostly in Africa, building health facilities. And also Laura Stachel of We Care Solar was incredibly helpful, because I'm not a medical expert, so I'm an energy expert. So we relied on them entirely for creating this table that I'm about to show. So when you click on one of these buttons up here at the top, it populates this table down here, and it's really just meant to be a default or a template. It's not saying this is what you should do, but it gives you a head start. And if, for example, you say, no, we really have 2 vaccine fridges, fine. Oh, and actually we look at it, no, really they have 80, their nameplate power is bigger. You can edit almost all these things. Things like a fridge should be always on. But it has a duty cycle. So the average power you can see is less than the nameplate power because it's always plugged in, it's always staying cold, but the compressor is going on and off. So that's why the average power is less than the nameplate power. But for other equipment, it's not necessarily always on. And so to make it simple, we just broke the day into 3 time periods, day, evening, and night. And of those 3 time periods, how many hours is it on during those periods? So if it's always on, you can see that adds to 24, right? So lots of different equipment here. You can, collapse and expand them as possible. And you're going to want look at this and make sure it makes sense for your facility. But you can also do things like, well, if I were to buy a bigger air conditioner, let's say, what would that do to my energy requirements and the size of the power system I might need, et cetera. So we have we have a lot of stuff here. We have even, you know, housing for the staff, water pumps. Again, this is just 3 classic sizes, and presumably you don't have all 3. You have one. Pick one depending on, and you might need to modify the size, of course. Most importantly, you can add anything you want. So this is, you know, your special whatever equipment. And then you have to say how big it is, how many of them, how big they are, does it have a duty cycle, and how often when does it run? And you can do as many of these as you want. So when you've got this all set up, you just hit calculate, and I'm going to cheat here like they do on cooking shows where you put it in the oven and then suddenly the turkey's all done. Here's what you get when you're done. It doesn't take that long. It takes maybe a minute or 2 to run. And so we have 4 different what we call architectures or configurations. You know, this is the full hybrid system with a backup generator. Here's the same thing without the backup generator. Here's just if you ran just with the genset alone, or if you add a battery to the genset. And they're ranked by net present cost or cost of energy. And you can see the one with the backup generator is the least cost system, even though the backup generator only runs 212 hours a year and only uses 227 liters of fuel. So you can design a system without a backup generator, but it's going to be a lot larger, a higher capital cost. And so that's up to you whether it's worth that or not to avoid the hassle of having a backup generator. But it will, the backup generator, even though it doesn't run very much, saves a lot of capital cost. But you can see compared to the pure generator system, which has a very low capital cost, but very high operating costs and cost of energy, et cetera, this is preferable. So you can further get a lot more results by clicking on any one of these 4, and that takes you to, let me just make sure that takes you to here, which is a lot of detailed results. And I won't go through all of them, but here's the cost breakdown by type, by component. Here's where the power came from, and you can see the generator is mostly used during the rainy period, which makes sense. And lots of information about how it ran. We also have a report here. Here's a list of all the inputs. Again, and what I think is really valuable is, it is the ability to download the, so when this ran on the server, it ran Homer, and it created a real Homer file, which I've downloaded over here, and I can view that in, let me pull it up here. Hopefully you've all been seeing what I've been showing.
Peter,
Yeah.
we're not seeing it. I think you need to share your entire screen instead of just the window.
Right. So were you seeing what I was showing before, hopefully?
Yes.
We were seeing the entire application, but
good.
not seeing the document that you put up at the beginning. That
Yeah.
did not show up.
Yeah, well, that was okay. I figured that wasn't working, and you didn't miss much there. So you should be seeing my whole screen now. And here is home here. So I downloaded the file that was created on the server, and I opened it on my computer, and this should have the same results. It'll be in a slightly different form, but this table down here is the same one that we saw on the website, almost exactly the same. We modified it a little, and here's where you can dig in more detail. Again, this is just formatted differently, but it's the same information I showed before. But what's really interesting is you can actually go in and see how did the system actually operate across the whole year. You can zoom in. I'm going to wrap it up a little bit here, because I can get carried away because there's an enormous amount of detail that we can show here. Like there's the solar resource for the whole year, 365 days of the year, 24 hours of the day. Each one of these little colored dots is an hour. So here's like right here is like a 3-day cloudy period. And we can do that for all the different variables. Here's what the load looked in the same way. We can look at daily profiles. We can get really carried away here, which I don't want to go too deep into it. We have a 21-day free trial for those. Well, the web app is free. Just you can go on the web and use it. To pull it up in Homer in the desktop software, there's a 21-day free trial. So we encourage people to use that. I'm going to wrap it up there and open it up for questions.
Thank you. Thank you, Peter.
Well, you're welcome.
So,
and I haven't been monitoring the chat. Oh yeah, here, there's questions in the chat. So I'll work backwards, I guess. Is the data in the load profile assuming all is AC powered, no DC equipment? You know, that's a big question, and that came up a lot. And yes, it does. Well, what you can do, there is a way to includes monitoring system in that Word document. Hopefully, is that still up here? There is a way to use this tool to model a DC system. Not if you wanted to, in the desktop app, you can have a DC bus and an AC bus. You can have loads on AC loads on the AC bus and DC loads on the DC bus. In the web app here, we don't have that ability. Let me pull this up here. In the Word document, we do talk about how to do that, how to model a DC system. I haven't looked at this Word document in a while. Here we go. DC system considerations are discussed further below. So rather than try to read this in real time, we do have a way of doing that, of modeling a DC system. If you want to model a system that has some DC loads and some AC loads, you need to use the desktop app. Okay, so wait a second. I need to start at the top here. Here, well, so you can see what I'm looking at. Is the cost of fuel customizable? Yes, that's easy to show as well. Right here. In fact, I did that. I reduced it from $1 a liter to 75 cents a liter. And actually, we have 3 different fuels here. In the desktop app, you can create your own fuel, you know, as well. So you could do high sulfur diesel or low sulfur diesel, etc. We have a new question here. Is the user able to modify the utilization factors for each of a piece of equipment? You mentioned refrigerant cycle as an example. Yes, well, so in the desktop application, you have an enormous amount of flexibility to define the loads, but you don't have a table like this of appliances where you see here we've made it easier by creating this table of appliances. You're talking about utilization factor. Well, I think I use the term duty cycle. I think we're talking about the same thing. So, for example, here we're saying this vaccine fridge has a nameplate power of 80 watts, but the utilization factor is only the compressor is only running half the time. If you think that utilization factor is way off, you might want to come down here and your refrigerator, create your own refrigerator, and let's say that's also 80 watt nameplate, but you think it only runs a quarter of the time. There you go. And then but you want it to run, it's always on. So yes, you can do that, but you have to create a custom equipment to change the, if I'm understanding what you mean by utilization factor, that's for something that like runs off a thermostat or something that comes on and off by itself. The other thing that utilization factor could mean is just, well, how much is it used? Like it's only used 2 hours out of the day. You can, all these fields that are in a little box are editable. So somebody's asking us about projects. Well, we don't actually build systems. We have the software, and we distribute the software, and this web app is free to use. Now that we're part of UL, Underwriters Laboratory, they have a large advisory services group, so we can help people in a variety of different ways, be an independent engineer, an owner's engineer, help them do the analysis, designing systems, etc. But Underwriters Laboratory, actually, I should give a little history about it. It's been around for 125 years. In the US, it is the main organization that certifies electrical equipment. So if you want to sell a toaster in the US, you need to get it UL approved. So it's really important that we maintain neutrality. So we don't build systems and we don't sell equipment. We're technology neutral, vendor neutral, etc. So our customers, our users, are the ones that actually build systems. And we have, this person's asking about Uganda. We have hundreds of users in Uganda, and actually every African country, some more than others, obviously, but the software itself is not open source, although, like I say, the web app is free to use, and the desktop app, it comes with a 21-day free trial, and we have discounts for academic users and students, etc. How large a system can be modeled using this system, using this capability? Well, there's no real limit on the desktop side. On the web app, this system here is a reasonably large hospital, and it's total, going down to the bottom here, total 360 kilowatt hours per day, so that's 10,000 kilowatt hours a month. You could model something larger than that even as well. I think the main limitation on size is that we're assuming a single backup generator. So when you get to really large systems, you're probably going to have more than one backup generator. And I don't just mean for redundancy purposes. You probably want more than one anyway, because if the one's on maintenance, but they might be identical and they never run at the same time. But in really large systems, they have multiple generators, and they can either parallel with each other or they're different sizes. They're not just for redundancy purposes. So anyway, we have used Homer to model islands the size of Aruba or Maui or St. Thomas You know, that's 100 megawatt, 150 megawatt systems, much larger than you'd want for a rural health clinic. And the desktop app, you can have as many generators as you want, but on the in the web app, we're assuming a single generator. That's the main limitation on size, I think. So let's see, and there's no other questions coming in through the chat. How am I doing? Oh, got lots of time. I think what I'll do then is show you. So for this larger hospital, I haven't modified it in any way, just to show you. It takes, like I said, a minute or two to run, and so I might as well show that. So this system was imagining having 357 kilowatts of PV if you were trying to do it without a generator. With the generator, of course, the PV and the battery can be a lot smaller. I think it's worthwhile to show some of the other results that you can get out of it. Like, for example, the batteries are a really critical issue. So we were talking about 14 batteries. In reality, you probably want to redesign things so that they're in strings, and 14 is kind of might not configure into strings correctly. So that's where during a final design you would want to use the desktop app. Our target market for this are the planners, the people or the healthcare facility manager, whoever that is, who may not really be an energy expert but wants to get some idea of what's possible. And then he's going to want to talk to, or she is going to want to talk to a local solar company to do the installation. But it's enormously helpful if they already have some idea of what they need, both in conversations with that solar installer, but also in conversations with funding organizations. Like this system was going to need, I can't remember, $20,000, I think. Without something like this, it's hard to have a conversation with a funding organization about, well, we need a power system. How much is it going to cost? You know, you need to have some information to answer those questions. So now we are getting some more questions here. Is there a user group to help people learn best practices for different communities? You know, that's a great suggestion. That's a fantastic suggestion. And I'm going to talk to the World Bank about that. They are the ones that funded this. So there isn't a user group at the moment, but you're right, there should be one. And it just needs, it doesn't need a lot, but it needs a little bit of funding just because somebody needs to manage that. So that's a great suggestion. Actually, we probably should have done it ourselves. We have been asked for assistance in designing microgrids around the world. Can we use Homer to design these systems? Absolutely. Absolutely. That's exactly what we do. And now that we're part of UL, we have offices in South Africa. We have offices throughout Southeast Asia, Australia, a couple in Latin America, you know, actually a fairly substantial office in Barcelona and in Singapore that support those other offices, and Dubai. I think there's 100 offices in 100 different countries. So we and we also now, which we didn't before we were part of UL, we have a substantial advisory group. You know, consultants, people who could actually help you with that. And in the past, we just provided the software, but now we have the ability to provide more services to support the software. Do you have a list of users in different countries that can be contacted? Well, there's a privacy issue there. We do have that list of users, and we can contact them, but the world, especially in Europe, have gotten very sensitive about privacy issues and passing along contact information. So we so that's something we'd work together with. We can contact them for you. How do we find the UL services? Well, on our website, maybe I'll just go to our website here. We have services, and there's training, of course, and support. So just contact us, support@homerenergy.com, or sales@homerenergy.com, or Peter. You can contact me at homerenergy.com. What's the next one? What does the emission measurement for pollution represent or stand for? Well, let me remember what we did on the website. I don't think we did much on the website with emissions. Let me just go back up here. No, but in Homer proper, we do a lot with emissions. You can put in a carbon tax and see how that affects the design, the least cost design of the system. You can put a constraint on the design that says, okay, design a microgrid that emits no more than X amount of carbon. You can do a sensitivity on that number and create a graph I find very interesting that shows that the least cost system produces a lot less emissions than a pure diesel system. By adding more and more PV and batteries, you can reduce the emissions even further. It gets very nonlinear as you try to go to zero. And that's a really useful graph to look at. And you can do the same thing with any of the other, like nitrous oxides and sulfur and particulates and volatile, any of the emissions. Most of the interest is in carbon, but you can do it for any of them. Ethanol in the desktop application. So in this application, we have these three fuels. Propane's a pretty common one, frankly, or LPG. I guess in most of the world it's called LPG. The purpose of the web app was to simplify things, so you don't give it. If you give people too many options, it gets too confusing and hard to use. So we want to make it easy to use. Desktop application, yeah, you can use ethanol, and you can create your own fuels as well. What is the cost of desktop application? Well, it depends on which modules you get. And it depends whether you have a monthly, 1 year, or 3 year license. So a 1 year license for the base version of Homer is $500. The monthly one, I think, is $65. For the commercial version, academic users get a half price, and students get 75% discount, 25% of the. So instead of $500 per year, it'd be $125 for a whole year, or something like $15 for just a month for a student. So we have a range of, we have quantity discounts. We have concurrent users, which for classroom use is so we can set up well, actually, classroom license is different than a concurrent license. I'm sorry. We have many different licensing options. So you're asking for cost for educational institutions. I don't have that number off the top of my head. If you wanted to set up like 20 instances of it, like in a computer lab or something like that, we have a huge discount for that, but I don't have the number off the top of my head. for one researcher at a professor or something at that's half price. Am I answering all the questions? Did I miss any? No, I don't think so. Right. Right. Actually, I'm sort of curious for the people on the call, how many of them are involved with designing or rural health clinics? It's such a crying need. I don't know the best way to get responses on that question, but
Can you hear me? Hello?
yes. Hi.
Okay. Yes. Hi. Yeah, we are working. We have a interesting project in Kenya, and this is around a health center in a rural area. So what you're talking, this software, I mean, it comes in perfect. It just right on the spot. I don't know if Billy is connected. Billy, you may want to ask Peter some questions of maybe how we can work with him. I don't know, Billy. Is Billy connected?
Who is that? I'm sorry.
Yeah, Billy Gibetti. He's a researcher here at the UNM, and he's the lead for a project in Kenya around a health center. And so he's and I think he's connected. And Billy, you may want to unmute yourself. And Hillman has raised his hand. Hillman, do you want to unmute yourself?
Yes, this is Hillman Mitchell. Yeah, I do work with.
I think I had you.
Oh, sorry. Go ahead, Billy.
Yeah, I missed it.
Billy, we lost you. While he connects, Hillman, go ahead.
Yeah, excuse me. I do work with a group that works on designing limited access rural hospitals in the U.S. And so this is a very effective tool to help in sizing and determining operations of various types of energy sources to ensure that they have power. So thank you. This has been a good session.
When you said limited access, we're talking about health facilities in the U.S. or you're designing them in the U.S. but they're what kind of facility were you referring to?
Yeah, so this is for rural hospitals in the U.S. that typically are in areas that are, for a variety of reasons, need to have more sustainable energy sources, mostly due to costs. So many of the rural hospitals are really stressed, especially during this time, but in general, they've been losing funding and they tend to have facilities that are older. And so we're working with various groups to try to design and build. But we also look at that from the international perspective as well. But we're starting off in the U.S. and then propagating that to other countries.
We've done a lot of work in Alaskan villages because there's some really remote. There's like 200 remote villages in Alaska.
Mm-hmm. Yep.
But there we actually work with the local utility company to make the whole village system more sustainable. And similar with like islands that we've worked in. But usually the facility they care the most about is the hospital. Yeah.
Yeah, absolutely. This is a good tool. So thank you.
Peter,
This is Billy again.
Billy,
We can't hear you.
I started to hear someone.
Billy, can you hear us?
Can you hear me?
Yes.
Now we can.
Yeah. Yeah.
Oh, you're muted.
You're muted.
Am I?
No, now you're not.
Okay, let me try to see.
No, you're
what
good.
happens.
You're good. You can talk. Go ahead.
Okay, so I was responding. I think what Ramiro said. We are putting up a health center in Western Kenya. And so the question I wanted to ask is, if we need to install backup like you are describing for this, because it's unreliable, power in Kenya is unreliable, sustaining the power needs. Would we go through, I saw you work with USAID, or how could we get that partnership?
Well, our USAID was really, really helpful 15, 12, 13, 12 years ago, creating the original version.
Uh-huh.
The way USAID works is projects are all funded out of the local missions. So you know, even though theoretically I've got access to their headquarters in Washington, the local office in Nairobi is actually the one that's more that has access to funding. But I wouldn't just focus on USAID. There's lots of organizations with an interest in this. UNDP, UN Development Program, was actively involved in this. The World Bank was the main funder, and they funded a mini grid. What do they call it? Mini grid learning event. So I was in Nairobi for that. It was probably a year and a half ago or so. But they have an active programs to promote these mini grids and microgrids throughout Africa. We've done the same thing in we did with Kenya, Ethiopia, Ghana, Nigeria, Myanmar. I think those are I know there was one more, Tanzania, I think, as well. That was the first one. That was actually before I got involved. So the World Bank has that's the program I personally know the most about. But the UK aid agency is promoting microgrids. Actually, I went to Somaliland on a UK funded. That wasn't focused just on health clinics. It was on mini grids for the whole village. I mean, one thing that this app doesn't do, but it's a really interesting idea though, is so if you've got a health facility without power, that means that nobody has power, yeah, right? And if the health facility, if it is right in the village, if there's other, houses or maybe a school or commercial, little shop or workshop or some commercial activities that are close by, then instead of just building a power system for the health facility, you can create a small distribution system and provide power to nearby and other buildings, whether they're houses or whatever they are, schools, whatever, nearby, and have it be the locus for the whole community. It depends on the sort of the layout of the community. For households that don't need a lot of power, they just want some lights and maybe a small TV or something. They're probably better off having their own solar system unless they happen to be really nearby. So that's the kind of that's where you want to pull in a local developer. And I know in Kenya there are several companies that are very active in developing these. Power Gen's one, Power Hive. There's several. And there's a whole African Mini Grid Developers Association. I think it's based in Nairobi. That with members all over the continent. So this is a really growing field. It's so encouraging to me because I've been talking about this literally since the early 90s, thinking, well, there's so much potential here that, a billion people without access to power, that's a real tragedy in a way. That means they don't have access to healthcare. They don't. You can't get a teacher to stay in the community if there's no power. And people move to the city because there's no economic activity that would require power. And so I've been talking about this for almost 30 years, and it's just now really taking off. So it's very, very encouraging to me to see that. And COVID might actually be the spark that makes things happen faster, because healthcare is probably the most important single use or need for electricity.
Correct. We also have a partnership with Engineers Without Borders, so that's something, a group network that we can work with. If I'm sure the World Bank has some finance for these type of projects now because of COVID. If you have any information that you can share, that'd be awesome. And then we had another collaborative a couple of weeks ago, and there's a fund, humanitarian fund, available for these projects, and those people that participate, please go to the IFE's webpage. There's a collaborative, and it gives the instruction how you can apply for this fund, which 60% of the fund is forgiven, and 40% can be paid back zero interest for, I don't know, 20, 30 years. That's something. So there are mechanisms, and I think this tool, Peter, I think this is something that we need, because energy right now, especially because of COVID, you can't do anything. We don't have energy, and then energy is connected to telecommunications, so they go hand in hand. So we need both systems to deliver good healthcare around the world. So this is perfect.
Yeah, and thanks for mentioning. Thanks for mentioning telecommunications, because I should have mentioned that. That's actually there. Boy, I mean, there's cell towers going up all over the world, and especially in Africa and other parts of the developing world, and they all need power, and that often is the anchor tenant for these. And huge logistical challenge if they try to power those cell towers with diesel. Just keeping the diesel fuel supply going on a continuous basis is just a huge challenge, and these predominantly solar microgrids are much more sustainable, both environmentally but also just financially and logistically. They're just preferable in a million ways, and they can be the same kind of anchor tenant for electrifying the community, depending on like where the tower is, et cetera. So yeah, telecommunications, I should have mentioned it, is right up there with healthcare and education and commercial productive uses. Well,
Hillman,
listen.
Hillman has a question. Go ahead, Hillman. You have see your hand raised. If not, we're gonna.
No, sorry,
Okay.
Romero. I was just raising my hand to indicate when he asked the question if anybody is actively working on designing healthcare facilities. So, sorry, I'm good. Thanks.
Okay, so we're gonna wrap it up. We're almost an hour. I want to thank Peter for your presentation and the tool that is available. We will be reaching out to you. There's several organizations that will probably use the software that you have. Health, we launched Peace Engineering Echo about 2 months ago. And the program where we connected is Health, Wellness, and Peace Engineering, and has gone global. We are connected with the ECHO network, which is one of the largest health networks in the world. And this is something that we can talk offline. But I want to thank everybody for participating. Thank you again, Peter. Everybody, thank you. Stay safe. there's the contact information. There's the website where you can look at the webinars, the collaboratives that we have produced on funding, on water, etc. There's my email that you can send me an email, and several other websites. So we need to. There's no time to wait. I think the world has called for us to take action, and let's do it. So thank you, everybody. Thank you, Peter. Everybody, stay safe and happy holidays.
Yes, and thank you all. I really like connecting with people all over the world to talk about clean energy, how to provide clean energy to everyone everywhere. So thank you for coming. I appreciate, and feel free to contact us. We always like contacts.